Hi everybody, this video is going to be about the method of Lagrange multipliers and how we can use that for optimization problems. To begin, we'll refresh on how we've done optimization up until this point. So starting back with the single variable case, we had some quantity q that we'll want to maximize or minimize, potentially a function of many variables. And we really needed constraints, not only because of whatever problem it was we were trying to solve, but the constraints were necessary to us to get the function down to a single variable function. And once we had a single variable function, we could use methods from single variable calculus to find the maximum and the minima. So say where the derivative doesn't exist or equals 0, and then we could use second derivative test to evaluate whether or not we were dealing with maxima or minima, barring having access to a graph. And so we could use stuff to figure out where the high points or low points were. Once we know how to deal with functions of multiple independent variables, we took those constraints and substituted them in for whatever our quantity was to generate some function that obeys whatever our situation needed to be for the problem. And then once we've got that function, potentially of many independent variables, that's okay. So we've got some, say, surface or higher dimensional object, and we could use multivariable calculus techniques, say, figuring out where the gradient was 0 or didn't exist, and then using second partial test to determine whether we were dealing with high points or low points that we found. And we could find the minima or the maxima. Okay. But I'd like to look at what's going on geometrically in terms of those constraints. So we've got some function, and for this we'll talk about functions of two independent variables, although this will generalize nicely to higher dimensional stuff. For the purposes of being able to visualize these things, we're going to stick to two independent variables. So we've got some function f of x and y. That's our objective function. That's the thing we want to maximize or minimize, find the high or the low value of. Subject to some constraint, I'll call it constraint function g, where g equals 0, and whatever constraints you've got in terms of x and y, you could write some function g that equals 0, and that's going to be important to us a little bit later, as we'll see. But let's notice the dimensional mismatch that's going on here. So f, I could say z equals f, and what f really is some surface. But g, on the other hand, there are no z's here. It's just a relationship between x and y that I need to hold. So what I've done here is project this down onto the bottom of the box, but you can imagine that that's just a graph relating x and y in the xy plane. And so if the constraint is just restricting which x and y pairs I'm allowed to even consider, then really if we're looking at our function that we're trying to maximize or minimize, what that constraint is doing is just limiting some portion of it that we're able to look at. We're only allowed to look on our surface in this region, on those points that are black. And as it turns out, the high point or low point of the region specified by the constraint, g, those candidate for high points and low points are going to happen where the level curves of f are parallel to the function g. So those places where the level curves of f are parallel to g are candidates for high points and low points. Well, if we're looking for places where the level curves of f are parallel to the graph of g, we know the gradient of f is always perpendicular to those level curves of f. And we can think of g as a level curve itself of some other function. And so if that constraint G is a level curve, then the gradient of G will be perpendicular to the graph of G at every point. So what I've got then is the gradient of f is perpendicular to the level curves of f, and the gradient of G is perpendicular to G. If I'm looking for a place where the level curves of f are parallel to G, then finding a place where the gradient of f is parallel to the gradient of G, that will, because those are each perpendicular to the things that I care about, then when they're parallel, so then will be the level curves of f and G. And that is what I need to make sure happens, is that the gradient of f needs to be some scalar multiple of G. I've written the scalar here as some number lambda. So they don't have to have the same magnitude, they don't have to point in the same direction, they just have to be parallel, and as long as one's a scalar multiple of the other, then they will indeed be parallel. And if those gradients are parallel, then the level curves will be parallel to G. So we define a new function called the Lagrangian in terms of x, y, and that scalar multiple lambda as just f minus lambda g. Where we call that lambda the Lagrange multiplier. And the solutions of the gradient of the Lagrangian being equal to the zero vector is what's going to give us candidates for our extrema. Now remember, the Lagrangian's a function of three variables, so that gradient is going to take into account all three of those variables. Namely, what we get is a system of three equations and three unknowns. So the partial of the Lagrangian with respect to x has to be 0, the partial of the Lagrangian with respect to y has to be 0, and the partial with respect to lambda, which just ends up being negative g, also has to be 0. So that's three equations and three unknowns. How does this line up with what we talked about? Well, notice that the first two are really just the statement that the gradient of f is parallel to the gradient of g. And the second one is just our constraint equation, just our constraint condition, namely that g is 0. So this ties up all that information. And note that we don't really care about the value of the Lagrange multiplier. I don't really care about the value of lambda. I just need there to be some lambda that makes this work. What I'm interested in, again, are the values of x and y, where f and g are, where the level curves of f and the graph of g are parallel. And this helps me find that. I might note that there's one rare case that would be a solution that we haven't really talked about, and that is, what if the region specified by the constraint just happened to pass through what was already a relative minimum or a maximum of f. Well, that's tied up in this, because if that were the case, if there were a spot obeying our constraint where f was already actually was its minimum or maximum somewhere along that constraint, then the gradient of f would be 0, and that case gets caught here if lambda is 0. So we'll sort of catch any possible way that we have a high point or a low point on our function f by looking at this gradient of the Lagrangian being 0. So here's an example. We've got some objective function. I want to find the maximum value of this function subject to this constraint. So take a moment and see if you can figure this one out. Feel free to use a calculator, Wolfram Alpha, some sort of assistance if the algebra gets a little bit messy. And it's also worth checking via the second partial test once we identify a candidate for a maximum to indeed make sure that it's a maximum. So take a moment and do that. And the surface and constraint we are talking about are pictured here, and unless I made an algebra or arithmetic mistake somewhere, you should find that maximum near this point. All right, I'll see you guys in class.